Time. It's all around us. But is it what we think it is? Time seems to flow forward. But can it run backward? Do events unfold one after another? Or do past, present, and future exist side by side? It's one of the most challenging topics in science, questioning our most basic assumptions about reality. Is time a fundamental part of the universe? Or could it be that time doesn't really exist? Space, time, life itself. The secrets of the cosmos lie through the wormhole. What time is it? I could tell you it's 9:02 p.m., but your time may vary, depending on where and when you are. For most of us, time is a set of numbers we use to gauge our days. We live our lives by the clock, waking up, racing to work, going to bed, and on and on. It wasn't always like that. When I was a kid, summers were timeless. I had no particular place to be, no appointments to be kept. My days were bounded only by the position of the sun. Time didn't matter so much back then. Now my life is a race against time. But what am I racing against? Is time a real thing built into the universe? Or is it just an abstraction, something we humans created to keep our civilizations running? For the answer, we have to ask a deceptively simple question. What is time? Think about it. Try to define it. It's not easy.
Time is what keeps everything from happening all at once. And so time is that part of the world that orders events in a certain way so they happen sequentially from beginning to end.
What we're realizing in neuroscience is that time is not what we thought it was. Time is not something you're passively tracking. Instead, it's something that you're actively constructing with the brain. And my brain and your brain can be very different in terms of how they see the same event.
Time just does not exist. What exists is these distributions of everything in the world, these what I call nows. That's the real thing.
What I enjoy about time is the recording of it.
To Roger Smith, time is money. His custom-made watches sell for hundreds of thousands of dollars. The hardest part of the job is to get these jungles of tiny gears and wheels ticking at precisely spaced intervals.
To bring a watch to time, it can be quite a lengthy and complex process. And this particular wheel, it has to be perfectly balanced. And if it isn't perfectly balanced, then your watch will keep different rates, different times in different positions.
Roger's goal is to get his watches to match Greenwich Mean Time, the time that every clock around the world uses as its baseline. It was named after this place, Greenwich, England. Time as we know it was born here. In 1884, a world conference decided that the meridian line that passes through the observatory at Greenwich was to be the initial meridian, the master time for planet Earth. Greenwich Mean Time is our best approximation of time as described by Sir Isaac Newton, a steady beat pounding behind the scenes of the universe. Newton believed the universe was like a giant clock set into motion by God. But Newton got it wrong. Lee Smolin is a theoretical physicist trying to solve the mysteries of time.
Newton's concept of time was that it was absolute. It was like a metronome, which, as he said, ticks on absolutely without regard to whether anything is happening in the universe or not. Even if nothing is happening, for example, even if in our studio here no music is playing, the metronome just kicks on absolutely at the same rate no matter what is going on. The problem with this is that it's actually impossible for any of us to detect absolute time. We don't detect absolute time. We detect time as relationships between things that happen. And we can illustrate this by asking the musicians to start up the music. And they start to play and they develop time between themselves, a relational time completely built from the relationships between the notes they're playing, the events they're creating. That's what time is really like. So we can turn the metronome off. In fact, we can just get rid of it. And the world keeps going on, the music keeps going on just as before. This was the great insight of Einstein, and it was the basis of his general theory of relativity. That time is created by the relationships of the changes that happen in the universe, and nothing else.
Even today, some people have a hard time accepting Albert Einstein's relational time over Isaac Newton's absolute time. But the better we get at telling time, the more we can see that Einstein was right. This is the aluminum ion experimental clock at the National Institute of Standards and Technology in Boulder, Colorado, America's official timekeepers. It's the world's most accurate clock, measuring the oscillations of supercooled atoms. It keeps time to within 1 second every 3.7 billion years. In 2010, Boulder's Time Lords took 2 ion clocks side by side in perfect synchronization. Then moved one of the clocks up 12 inches. The higher clock went out of sync. It beat just a tiny bit faster than the lower clock, because the higher clock is just a tiny bit farther away from the gravitational pull of the Earth, which slows things down. Einstein predicted this would happen back at the dawn of the 20th century, and he was just getting started. If we perceived the universe as Einstein pictured it, life would not have to flow in a smooth linear progression. A simple act could be cut up and rearranged with no logical direction backward or forward, no beginning or end. This is how the universe would look if we were physically unstuck in time. Sean Carroll is a physicist at the California Institute of Technology.
We live in space. All around us, there are 3 dimensions of space. What Einstein realized is that time is also a dimension. In fact, time and space are one thing called space-time, which is 4-dimensional. That's what we live in, that's what we move in and live our lives through. Einstein furthermore realized that gravity is a manifestation of the curvature of space-time. When you have stuff in the universe, when you have a planet or a black hole or some kind of mass or energy, it warps the space and time around it, and that's what we see as gravity. And it really is the space-time that gets warped. It's time as well as space. So if you travel close to a strong gravitational field, you feel the flow of time differently than in outer space.
The relativity of time causes a lot of strange effects, such as time running faster for astronauts than people on Earth. But Einstein's solution to the mystery of time opens up an even more challenging notion. If we look around, we see that all of space exists right here, right now. So doesn't it follow that all of time, past, present, and future, already exists as well? Could it be that the future is already here?
Physics says that all the moments of time are equally real. And that tempts us into saying that they all exist simultaneously, they all exist now. But that's not what it's like. Different moments of time are really like different places in space. They're not here, they exist, but they're somewhere else. The difference is that unlike space, we can't help but experience time one moment after the other. We can't go back to moments in the past, and we can't right now talk to moments in the future.
This sort of temporal dislocation seems to contradict the laws of physics and human experience. Or does it? Maybe not. This man would argue that the world is filled with people who are unstuck in time, and that time itself may be all in our heads. Is time the steady beat behind the universe? Or is time something that changes from place to place and person to person? The older we get, the faster the currents of time seem to carry us along. Our relationship to time changes as we age. Studies show that the passage of time seems to increase by the square root of your age. So if at 10 years old it's 1-to-1, when you're 20, it's 1-to-1.14. And by the time you're 60, it's 1-to-2.44, about 2.5 times faster. We all experience time at 1 second per second, but it doesn't feel that way. David Eagleman of the Baylor College of Medicine has spent much of his career puzzling out how humans perceive time. He's found that our perception of time is governed by biological and psychological states.
Many people will wake up just before their alarm clock because as their body's circadian rhythm is moving along, the signals in their body tell them this is the time to wake up, and then they pop awake.
Our time sense can also be altered by things such as sensory deprivation, overstimulation, and altered states of consciousness.
So, for example, when people smoke marijuana, they sometimes feel like, wow, I've been standing here forever. How long have I been here? And it's as though their passage of time is going slowly. But it's not exactly about slow time perception. I believe it's about their inability to nail down a memory, a landmark of when they arrived there. And without that landmark, it feels like they've been there for a very long time.
If you've ever been in an accident, you might have experienced the strange feeling that the whole event was playing in slow motion. But unlike a narcotic haze, you recall everything in vivid detail. This is another case of memory warping time.
What happens during a really high-intensity event is you have an emergency control center in your brain that kicks into gear and lays down very dense memories during that event. So it seems like it must have taken a long time.
At any given moment, the brain processes and synchronizes an enormous amount of information. Simple acts are actually small miracles of the mind's speed and power.
When you snap your fingers, it looks like it's simultaneous. It looks like the sight and the sound are happening at the same time. But in fact, what's happening is your auditory system is able to take information coming in through the ears and process that very quickly, whereas your visual system is much slower. So what happens is your brain hears the sound and then it sees the sight, and somehow it has to take both of those and stitch them together and serve up a single story, which is that they were simultaneous, even though the signals are arriving at the brain at different times. This whole thing is really smeared out in time, and yet it doesn't feel that way to us. It feels as though the whole thing is simultaneous.
It takes a few millionths of a second for your brain to put together information and serve it up to your consciousness, which means that we're all living a tiny bit in the past. This time delay is the trade-off our brains make to give us the best story of what happened. But when the brain doesn't get the story right, it can change your relationship with time. Your personal time becomes different from others, and that can have very bad consequences. Medical journals tell of the strange case of the man who went for a drive and noticed that the trees and buildings by the road were speeding by, as if he were driving at 200 miles per hour. He eased up on the accelerator, but the cityscape continued to whiz by. This man perceived the world as having accelerated. In reality, he had slowed down. He walked and talked in slow motion. He had become unstuck in time. It turned out that his time sickness was caused by a brain tumor. Whatever time is, it's deeply wired into us. We are all clocks with our own internal time. David Eagleman suspects that going even slightly out of sync with the flow of time can lead to serious mental illness.
I think that schizophrenia might fundamentally be a disorder of time perception. So imagine if there were some deficit in your time perception where you didn't know if your own actions were coming before or after the sensory consequences. What would happen is you would have a very fragmented cognition. You wouldn't know which things you caused and which things you didn't cause.
To show how flexible our personal time can be, David devised an experiment that subtly warps a test subject's perception of time.
So imagine that I have you press a button and that causes a flash of light. Now I inject a very small delay so that when you hit the button, the flash of light comes, let's say, 1/10 of a second later. What happens is your brain gets used to that delay. It starts understanding that when it puts out this act, the sensory feedback is a little bit slower than it expected. So it starts adjusting to that, and it starts to seem simultaneous to you. Now, if I remove the delay, so now you hit the button and the flash happens immediately, you will believe that the flash happened before you pressed the button. This is exactly what happens in schizophrenia. Somebody will make an act and say, it wasn't me. I don't feel like I was the one who caused that.
Time seems to vary from person to person, and the elastic nature of our subjective time has caused David to wonder whether time is, in fact, real.
I think that time might be the most stubborn psychological filter that we have, and that when we start really reaching down below that, when we start really figuring out how time is constructed by the brain, we're going to have to go back to physics and rejig all of the equations there.
Is it possible to eliminate the human factor and pull time completely out of our physical description of the universe? This man says yes. He's rejigged Einstein's equations, and he's found that time may not exist at all. Declaring that time is an illusion may sound radical, but the denial of time is an old idea, 2,500 years old. In 500 BC, the philosopher Parmenides declared that motion is impossible because for an object to move any distance, it would have to pass through an infinite series of fractional steps to get from one place to another. And no one can take infinite steps. And if motion is impossible, then change is also impossible. So, therefore, time must be an illusion. No one knew quite what to make of this. Surely motion is real. Things do change, and time does pass, right? Maybe not. In an ancient village in the English countryside, this man thinks that the laws of quantum physics prove that Parmenides was right. His name is Julian Barber. Decades ago, he began carefully laying out a mathematical case that the universe doesn't need time, which is a bit odd, as he's surrounded by the past.
We're standing in the town, which is a very ancient street, and behind me is my home, built 1659. Newton was 17 then, just seriously beginning to think about time and motion.
If time doesn't exist, what's all this? To Julian, everything we see is an archaeological dig. Things are there first, and time is deduced from it afterwards. He believes this 1,000-year-old church and these 14th century wall paintings are proof that the whole of time exists in slices of space.
Our past is just another world, or it's another possible configuration of the universe. It's another now. And this is literally true. The instant is not in time, time is in the instant.
Julian's radical view of time grows out of the Wheeler-DeWitt equation, a mathematical exercise from the 1960s that sought to reconcile Einstein's relativity with quantum mechanics. A strange thing happens when you do this. You're left with an equation that has no T for time. Since this runs counter to observable reality, most saw the equation as further proof that quantum physics and relativity theory don't play well together. But to Julian, it was a revelation.
There is no unique history in quantum mechanics. And if the evidence from the attempts to combine quantum mechanics with Einstein's general relativity is right, there is no time at all.
So at the deepest level of reality, time doesn't exist. What matters is how objects relate to each other in freeze frames of space.
My view of the universe is just like a huge collection of snapshots, which are immensely richly structured. They're not in any communication with each other. They're worlds unto themselves. But each world is so rich that it, so to speak, part of this world, it's snapshots within snapshots. This is really what our life is about.
Our brains assembled these frozen moments and played them in our minds the same way that still photographs played at 24 frames per second make the images you're watching now seem to move. But nothing is moving. What we call time is an illusion.
In some very deep sense, the universe, the quantum universe, is just static. Nothing changes.
And according to Julian, all of these snapshots of the universe exist simultaneously.
If I were to say that my yesterday no longer exists, it would be like the number 13 saying that 11 has died. Mathematicians would regard that as ridiculous. This instant is so vital and so alive, but in a way it's eternal. This is when you translate that into mathematics, it's eternal.
Julian Barber's view of time may sound radical, but is taken very seriously by the physics community, which doesn't mean everyone agrees with him. Far from it. Julian's close friend Lee Smolin is also one of his biggest critics.
Time is not an illusion. Time is not a construction. Time is not emergent. Time really is real.
The idea that time is an illusion has ignited a civil war in physics, a war that pits friend against friend. Is time an illusion we create to make sense of the universe? Neurologists and physicists say it might be so. But there's another camp that says we can't ignore what our senses and observations tell us, that time really does exist. In this view, we experience the world as a flow of moments because that's the way nature is. Passage of time is a basic truth, and in fact may be the one true thing in the universe. Tim Maudlin is a philosopher of physics at Rutgers University.
To say that the passage of time is really an illusion suggests that it's not really the case that I'm getting older all the time, that I should be worried that my death is every day, one day closer to me, and so on. But I just can't believe that. As hard as I try, I can't believe it. It doesn't fit with the world I live in.
For Tim, it is just common sense that time exists. So why do some physicists deny it? Tim thinks it's an occupational hazard of working with math.
Our representations in physics are all mathematical, and mathematical objects are not in time. Mathematical objects don't change. So if you work too much with numbers, and numbers don't change, and you're using that to represent the world, it might seem hard to see how the world itself can really be changing. People seem to be stuck on the idea that the world has the features of the mathematics that they use to represent it. That allowed people to get carried away with their mathematics and lose sight of the physical world.
Julian Barber believes space is all there is, and time is an illusion. Tim says Julian has got it all wrong. We need time, but we don't need space.
You can make space not fundamental, but time remains fundamental. There doesn't have to be anything more than time. And you can't do it the other way around. You can't start with space and then get time. So time is at the very bottom level. I think even this is what the physics is telling us, although we haven't been paying enough attention to it.
Did space come first? Or did time come first? This argument leads all the way back to the explosive birth of our universe, the Big Bang. Physicists agree that the Big Bang created space. They don't agree on whether it also created time.
There's a lot of people in physics and philosophy who think that time is an illusion, that what's really true at the deepest level is timeless, is outside of time. And I don't believe that. I used to believe that, but I've come to believe that time is really real.
Lee Smolin believes that time is older than the universe. It was here before the Big Bang, and it will be here after the universe ends. And he thinks he can prove it by looking closely at how particles of light behave over long distances. One of the core laws of physics states that light travels at 186,282 miles per second. If time is an illusion, then this will be true everywhere in the universe, no matter where we look. But if time is real, it's possible that the laws of physics have changed as the universe has aged. If a basic law of physics, such as the speed of light, doesn't hold true out in the oldest part of the universe, we'll know that physics has evolved since the universe was born. So time can't be an illusion.
There should be some experiments where if you look very sensitively, maybe the speed of light is not universal. And there are such experiments which are being done.
The Fermi Space Telescope is one such experiment. Fermi records gamma ray bursts, strange blasts of energy from the farthest reaches of the universe. These bursts give us the chance to check out the laws of physics as they were 13 billion years ago. Imagine two photons race out of a gamma ray burst 10 billion light years away. One photon bursts with more energy than the other. In our part of the universe, both photons will travel at exactly the same speed. But if the physics of light are different in an older part of the universe, Lee believes the higher energy photon should fall slightly behind.
It would break down at the point where after 10 billion years, one of them would be a second or 2 or 3 seconds ahead. But that's enough to be detected. Even 1 second worth over 10 billion years, we can detect that.
The gamma-ray burst data from Fermi will come in over the next few years. Lee may soon have his proof that the now of 13 billion years ago is truly different from our now, and therefore, time must be real. Conclusive proof that the laws of physics change over time would settle the debate over whether time is real or an illusion. But it still leaves a big question unanswered. Why is there time? In theory, physics doesn't seem to need time, and yet we feel ourselves moving through it. If time wasn't born in our minds, then where did it come from? Sean Carroll thinks he has the answer. But it takes an evil twin universe with backward flowing time to make it all work. Theories abound about how time works, in the universe and in our minds. But it's a rare physicist who asks the question, why is there time? If time isn't something we humans invented, then where did it come from? Sean Carroll thinks he knows. Sean is a theoretical physicist at the California Institute of Technology.
Time is real. We use it every day. The evidence is all around us. But as scientists, the more we think about what time really means, the more mysterious it becomes.
Sean accepts the common sense idea that time moves forward from the past to the future, like an arrow. But why does time have a direction? Sean believes the answer is closely tied to something called entropy.
What makes time special is a law of physics, the second law of thermodynamics. The second law essentially says that as time goes on, entropy increases. Entropy is telling us how messy things are, how disorderly, how chaotic things are in the universe. So in the past, if you go all the way back to the early universe, it was very organized. It was like this delicately arranged configuration of billiard balls. As time goes on, it's like we're playing pool. The first thing we do is we increase the chaos of the universe. As time goes on in the universe as a whole, disorderliness, entropy, goes up.
Since the explosive birth of the universe, the increase of entropy is the reason why the past is different from the future. Why there is an arrow of time. Why we remember the past. Why we grow older. Why evolution happens the way it does. It's all because of this increase of entropy.
So where's the mystery? Entropy goes up as time goes on. But interestingly, in the fundamental laws of physics underlying everything around us, there is no difference between the past and the future. The laws handed down to us by Isaac Newton, Albert Einstein, even in quantum mechanics, you have no distinction between one direction of time and the other. So if you have a very simple physical system, like just 2 billiard balls, when you knock one into the other, there is no difference between one direction of time and the other. You could play that movie backwards, it would look perfectly normal. It's only when we get to complicated macroscopic systems that there's a difference between the past and the future. When we have lots of balls on the billiard table, things happen in one direction of time but not the other. Or when all hell breaks loose in the pool hall. So now we have noise, breaking glass, blood splattering. These are all processes that increase the entropy of the universe. Together, all of these increases of entropy define the arrow of time. The question is, why was the entropy so low to begin with? Our universe seems to be out of balance. The far, far future is going to be a very, very disorganized place. But the far, far past was highly organized. As physicists, this kind of imbalance really bugs us.
Sean looked for an explanation of this imbalance of time, and he found it in the multiverse. According to this theory, the universe we see could be one of an infinite number of universes.
Imagine a mommy universe. So this mommy universe can essentially give birth to baby universes. A little quantum fluctuation can make a bubble of space that starts small and then grows, starts with low entropy and then increases in entropy, just like our universe does.
So, a mother universe gives birth to a universe like ours. a universe where the arrow of time moves forward. But to stay in balance, it also has to give birth to a mirror image universe where time moves backward. This means that in some other dimension, our universe has an evil twin.
Every bubble is its own universe with its own arrow of time. Within each bubble, the arrow of time seems fine, but if you compare different bubbles to each other, the arrows will be pointing in opposite directions.
Sean's multiverse theory has attracted a lot of attention since it was introduced. But will it prove to be the ultimate solution to the mystery of time?
Well, part of making progress in physics is saying, what if this is true, what if that is true? And sometimes when you say what if, you realize, oh, making that hypothetical leap really helps us with all these problems we're having. Other times, it just gets you in a mess.
Quantum mechanics and the multiverse theory give us interesting ways to grapple with the riddle of time. What happens when we add string theory into the mix?
Serious weirdness.
The mystery of time has many possible solutions. Time is absolute, or it is relative. Time is an illusion, or it is the very real product of entropy. But there is one other possibility, an idea that challenges our assumptions about yesterday, today, and tomorrow. To us, time seems to flow from left to right. But what if it also goes up and down? What if time, like space, has more than one dimension? A hidden dimension that we can't see. Steve Weinstein, a scientist at the Perimeter Institute, thinks it could be true, and that it may solve another great mystery, the riddle of quantum uncertainty. Steve is a physicist, philosopher, and professional musician. His view of time grows out of one of the most mathematically dense ideas in science, string theory. String theorists believe that space has more than the three dimensions we see. This got Steve to thinking that the same idea could be applied to time.
I thought, well, why do we multiply spatial dimensions so freely but not time? And, is there any good reason? So there was a sort of curiosity there.
Steve set to work. Time has always been treated as a line, a one-dimensional thing. But if time has two dimensions, then time isn't a line, it's a shape.
If you look at this guitar cable from far away, it looks like a one-dimensional object. It just looks like a line. If you get up close, you could see that it has another dimension, which has to do with the circumference of the cable. It's like a cylinder. Our world looks three-dimensional in the same way that this cable from far away looks one-dimensional.
According to Steve, if time has an extra dimension, then fundamental particles like electrons and photons are smeared across time.
So an ordinary way of describing a particle would be to talk about its position at any moment in time. So the particle or the pick could be here, or here, or here, or here, or here, or here. So if I were to graph that and I had the time as a vertical axis, I would just draw that. Now, if you have an extra time dimension, you might visualize the time dimension perpendicular to the guitar neck in this direction. The particle could be, it might be here, and it might be here, and it might be over here.
To put it another way, quantum theory tells us that subatomic particles don't have definite addresses in space. We can only guess where they probably live. Steve suspects they do have addresses, but those addresses are spread out across an extra dimension of time that we can't detect. If true, this revolutionizes physics. The fuzzy quantum world suddenly snaps into focus. But unfortunately, proving two-dimensional time is real may be next to impossible. For one thing, it's not easy to understand, even for other physicists. The math required to describe a universe with two dimensions of time is difficult. Add in the 9 spatial dimensions of string theory, and people's heads explode.
It's very challenging conceptually. It's the hardest problem I've ever worked on. And I think this is why more people don't do it. It's very hard to think in these terms. What would an extra time mean?
Nonetheless, Steve thinks it's worth the effort.
Multiple times is one way, possibly the wrong way, but it's a different way in a radically different way of conceptualizing the physical world.
The physicists exploring the mystery of time have very different ways of looking at the universe, but they all agree on one thing. We'll never solve the mystery if we don't do the detective work.
You have to work really hard, and you have to be prepared to fail over and over again and to make mistakes over and over again. But I think that wisdom also applies to the whole community of science. That is, we have to experiment with every stupid wrong idea before we get on to the right one.
Time may be real, or it may be an illusion. But from our perspective, the past is gone forever, and the future is yet to be written. Whether or not we discover there are physical aspects of time we can't perceive, our human experience of the endless cycle of life and death won't change. The golden summers of my childhood are gone forever. But there are new summers ahead, summers rich with the potential of things yet to come.